Example 2. So earlier in Module 1D, we saw how to use StatCrunch to perform regression on the exercise obesity data. Recall that we investigated the relationship between obesity and exercise rates, and recall that we checked conditions to determine that a linear regression was appropriate, including a scatter plot of the data, which appeared to be linear, and a residual plot, which didn't reveal any patterns, which is sort of a cloud of points above and below zero. So I'm going to give you the partial computer output on the next slide, and we're going to answer the questions that follow. Okay, so here's our computer output. We want to find the least squares regression line, find the critical value t star, what is the standard error of the slope, and construct a 95% confidence interval for the slope of the regression line. Now we could also find the slope of the y-intercept. This is not as common to do, so we're not going to do that, and AP would not expect you to do that. Okay, so what is the least squares regression line? So recall our form, and I'm going to use my variables, dependent variable, so exercise, change over to my white marker, so I'm going to put exercise equals, and I'm going to use my intercept, which is the 55.597, plus the slope is a negative 1.071, we'll say, times the obesity, which was just labeled obese. So make sure you saw where those coefficients come from. Not hard, and they do ask questions like this on AP, and you ought to be able to read computer output. So that part's nothing new. What's our critical value t star? So we look at our sample size. Our sample size is 53. Again, do not use that t statistic. Tempting just to go there and say it's 7.9, but that's our test statistic. And same thing with the p-value. We haven't talked about that yet in the context of this problem, but you'll do that with hypothesis testing. Our df is 51 because our sample size is 53. So I'm going to go to distribution menu, select the inverse t, 0.025, df at 51, and we get a t star of about 2.076. So what is the standard error of the slope? Okay, so the standard error of the slope, we look here for slope and standard error, and it's 0.1350668. And I rounded that to about 6 places. You definitely don't want to round to 1 or 2 places. Take it out 4 or 5 places. I went out 6 just to be sure. So part D, construct a 95% confidence interval for the slope of the regression line, and let's interpret. So to construct this interval, we're going to substitute the values into that form of b plus or minus t star standard error of the slope. And we have everything, so we have our slope at 1.071 plus or minus 2.0076 times 0.135067. And multiply the value to the right of that plus or minus to get the margin of error, which is 0.27116. So let's go ahead and interpret this. So we have our interval. So we're 95% confident. The interval from negative 1.342 to about negative 0.800 captures the slope of the true regression line relating to exercise, which was y, and obesity x. That's one way to interpret that. And the other way, which sometimes makes a little more sense in the context of the problem, is that we are 95% confident that each additional % increase in obesity rate, x, is associated with between a 1.342 and 0.80 drop in exercise rate. So notice example 3. A teacher wanted to know how well she could predict a student's test score based on their grade on an online practice test. She collected data on a random sample of 15 students shown in the table below. We want to construct a 90% confidence interval for the slope of the regression line and interpret it in context. So I'm going to read off these scores. So we have a practice test. I'm going to read off the practice test and then the test. So we have 81 to 85, 68, 75, 80 to 81, 74, 77, 98 to 93, 100 to 99, 86 to 88, 65 to 61, 70 to 75, 80 to 84, 74 to 78, 81 to 89, 89 to 85, 84 to 91, and 94 to 96. So before constructing the confidence interval, we need to ensure the conditions for the t-interval are met. And let's check these real quick. Again, if you need some details on how this is done, you can refer back to either earlier modules where we did this or within this module in the tech help. So the conditions need to be linear, independence, nearly normal, and equal variances. We'll look at these one at a time. So the linear, going to check this with the scatter plot and residual plot. It appears to be fairly linear. Residual plot doesn't reveal any patterns. So that's checked off. Independence, any reason to think they weren't selected independently? We're not given any reason, so that one can be met. The nearly normal condition, we're going to check with a normal probability plot. Roughly straight, a little bit of curvature in there, but nothing to raise too much of an eyebrow. So that one can check off. And then similar with equal variances, and we make sure that the residual plot, it doesn't fan out. So let's construct a 90% confidence interval for the slope of the regression line and interpret it in context. So while we don't have to do this first, I'm going to go ahead and run the regression on this just to get the line. And actually we need to do this before we run the residual plot, so you had to run the regression in order for it to be able to store all the residuals. So let's go ahead and do that. I want to look at the line, and then I'll run a confidence interval on that. Okay, so I can either select the regression number 4 or the regression number 8, the linear regression. Whichever you run, you're going to get a slope of 0.8 and a y-intercept of about 17.34. And so I can write that using my words, and test grade is 17.34 plus 0.801 times the practice test grade. And it's that slope that we're interested in running the confidence interval. So press Stat, scroll to Test, and select G, linear regression. It's quicker if you scroll up rather than scrolling down the whole way. Step 2, let's input the X list into L1, Y list into L2, if that's where you put it. And the confidence level here we're selecting is 90%. Press Calculate, and the interval along with some other values are going to be given. And briefly, we're given the slope, that B, the 0.8. We're given the degrees of freedom. We had 15, so DF is going to be 13. We're given S, which is the standard deviation of the residuals. We're given A, which is the y-intercept. We're given R squared, the coefficient of determination, and R, correlation coefficient. So how can we interpret this interval? We're 95% confident the interval from 0.629 to 0.973 captures the slope of the true regression line relating test scores y to the practice test score x. Or we're 95% confident that for every 1 point increase in the practice test score, the average increase in the test score is between 0.629 and 0.973. So let's go ahead and bump it up to 10 points. So you increase 10 points in the practice test score. The average increase in the test score is between 6.29 points and 9.73 points. I prefer the bottom two in context. We're kind of merging the two different types of interpretation, interpreting what the slope means with the confidence interval, sort of merging those together.